Coca-Cola is more than just a carbonated drink. It's a story of ingenuity, marketing genius, and global influence that has changed the way we consume beverages. The origins of Coca-Cola date back to 1886, when pharmacist John Stith Pemberton created a unique recipe that was initially positioned as a medicine, but quickly became America's favorite drink. From a small pharmacy in Atlanta, Georgia, to a global brand known in every corner of the planet, Coca-Cola has followed a path filled with innovation, challenges, and brilliant marketing moves. Its recognizable taste and legendary bottle have become symbols of a culture that unites people of different generations and continents. This story is not just about a drink, but about how an idea can become a global phenomenon, changing the world around it. Coca-Cola is a complex and carefully balanced beverage that combines several main ingredients, each playing an important role in creating its unique taste and texture. The base of the drink is carbonated water, which makes up about 90% of the volume. Carbon dioxide, dissolved under pressure, gives the drink its characteristic fizziness and refreshing effect, which is so valued by consumers all over the world. For sweetness, Coca-Cola uses either high fructose corn syrup or cane sugar, depending on the region of production. In the United States, such syrup is predominantly used due to its availability and cost, while in many other countries, natural sugar from sugarcane is used. These two sweeteners have slightly different taste profiles, which affects the subtle nuances of the drink's flavor, but both provide the same sweetness that millions recognize and love. The color of the drink is created using caramel color, which gives Coca-Cola a deep, dark brown hue. This coloring is produced using a special technology that ensures color stability and does not alter the taste properties. The tartness of the drink is provided by phosphoric acid, which also enhances the refreshing effect and gives the drink its characteristic light tang. Caffeine is another important ingredient that adds a slight bitterness and a stimulating effect to the drink. The most mysterious component is the natural flavors, which contain a secret recipe known only to a select few company employees. This mixture of essential oils, extracts, and spices creates the recognizable aroma and taste of Coca-Cola, which is impossible to replicate exactly. It is known that the composition may include oils of lemon, orange, cinnamon, nutmeg, and other ingredients, but the exact recipe remains a trade secret. In some versions of Coca-Cola, such as Coca-Cola Zero Sugar or Diet Coke, artificial sweeteners like aspartame and acesulfame potassium are used instead of sugar, which allows for reducing the calorie content of the drink without losing its taste qualities. These versions are aimed at consumers who want to reduce their sugar intake but do not want to give up their favorite taste. Thus, the uniqueness of Coca-Cola lies in the combination of simple but carefully selected ingredients, which together create a unique taste and aroma. Each component performs its role, from refreshing carbonation to sweetness, color, acidity, and subtle aromatic notes that make this drink legendary and recognizable all over the world. The production process of Coca-Cola is a true high-tech dance in which every step is performed with precision and care to create the legendary drink that is known and loved all over the world. Let's imagine we've entered a modern factory where the magic begins. It all starts with water, the main ingredient of the drink. Water comes from special sources and undergoes multi-stage purification. First, it is filtered through sand, carbon, and ultrafiltration systems to remove any impurities, bacteria, and unwanted substances. Then the water is treated with ozone or ultraviolet light for additional sterilization. The result is absolutely pure, crystal clear water that meets strict international quality and safety standards. In parallel, a sugar syrup is prepared. For this, sugar is dissolved in purified water in special tanks. This process takes place at a strictly controlled temperature to ensure the sugar dissolves completely and the syrup becomes homogeneous. The water for the syrup also undergoes filtration to avoid any impurities. The next key stage is mixing the syrup with a concentrate of aromatic substances, which contains the secret Coca-Cola recipe. This mixture is added in special proportions to create the characteristic taste and aroma of the drink. The result of this stage is the so-called blending syrup, the basis of the future Coca-Cola. Then the blending syrup is mixed with purified water and carbon dioxide in large mixing tanks. Carbon dioxide gives the drink its refreshing fizziness and a light tingling sensation that is so appreciated by consumers. The entire process takes place under strict control of pressure and temperature to ensure the ideal concentration of gas and uniform saturation of the drink. In parallel, packaging is prepared at the factory. Empty glass or plastic bottles, as well as metal cans, undergo thorough cleaning and sterilization. The bottles are washed in special machines where water under high pressure and temperature removes any contaminants. Then they are dried and prepared for filling. After this, the main conveyor process begins. Bottles move along belts at a speed of hundreds per minute. They are automatically filled with the finished carbonated drink through special dispensers that accurately measure the volume of each portion. After filling, the bottles are quickly sealed with caps or lids to preserve freshness and carbonation. Next, the bottles pass through a quality control zone, where special sensors check the fill level, seal, and absence of defects. If any deviations are detected, the bottles are automatically rejected. After this, the filled and sealed bottles move to the labeling stage. Labels with the logo, information about the composition, and expiration date are applied to them. Then the bottles are packed into cardboard boxes or plastic crates, which are convenient for transportation and storage. The packaged products are sent to the finished goods warehouse, from where they are distributed to stores all over the world. The entire production process is accompanied by constant monitoring and quality control. The factory has numerous sensors and computer systems that track temperature, pressure, carbon dioxide concentration, equipment cleanliness, and compliance with safety standards. This ensures that every bottle of Coca-Cola meets high requirements and provides consumers with a consistently pleasant taste. So, the production of Coca-Cola is a complex and coordinated work of a large team and modern equipment, where water, sugar, a secret concentrate, and carbon dioxide are transformed into a legendary drink. Bottles and cans, as if on a magical conveyor, go through all stages from cleaning to sealing, to ultimately end up in your hands, with a fresh, sparkling, familiar taste that has been bringing joy to millions of people around the world for over a century. In the first quarter of 2025, the Coca-Cola Company reported a net revenue of approximately $11,113 million, which is 2% less than in the same period last year. This decline was due to currency fluctuations and changes in the structure of franchising operations. At the same time, organic revenue, which takes into account internal growth without the influence of external factors, increased by 6%, indicating a successful pricing policy and a recovery in sales volumes in key regions, such as the Asia-Pacific region. The volume of sales in the form of product units increased by 2%, which is the best indicator since the second quarter of 2024, thanks to growing demand in India, China, and Brazil. Coca-Cola remains one of the strongest global brands with a recognition index of over 90 points, ranking among the top 10 global brands in terms of value and influence. The company is actively developing markets in countries with rapid economic growth, such as India, China, and Brazil, where the demand for soft drinks is growing due to the increase in the middle class and changing consumer habits. Imagine a cruise ship taller than 15-story building, longer than 3 football fields, weighing 70,000 tons. Now imagine driving at full speed onto a beach. That's how ships die. Every year, over 700 ocean giants make their final voyage, not to ports, but to demolition beaches in Bangladesh, India, and Pakistan. Workers with blowtorches dismantle these steel leviathans piece by piece, standing where waves meet rust. How does a vessel carrying 3,000 passengers become rebar for apartment buildings? What happens to the swimming pools, the engine rooms, the miles of copper wiring? Stay with us. You'll discover the brutal, beautiful process transforming floating cities into raw materials, and the shocking secret of why 95% of every ship lives again in different form. Our journey begins in Chittagong, Bangladesh, the world's largest ship-breaking beach. The coastline stretches 8 miles, littered with steel carcasses in various stages of dismemberment. From satellite view, It resembles a graveyard of metal whales beached in neat rows. Up close, it's controlled chaos. 15,000 workers crawling over hulls like ants dismantling elephants. The tide determines everything here. Ships arrive during spring tides when water rises highest. Captains gun engines to maximum, driving vessels onto mudflats at 15 knots. The impact shudders through steel bones. When tide retreats, the ship sits stranded, a beached giant awaiting dissection. Workers call this beaching. International shipping calls it the end. Before any cutting begins, the ship must be cleared. Imagine walking through abandoned cruise liner. Swimming pools drained, casinos silent, 3,000 cabins empty. Everything removable gets stripped. Furniture sold to local markets, lifeboats auctioned to fishing villages, artwork shipped to collectors worldwide. The chandelier from the grand ballroom? Now hanging in a Dhaka restaurant. Hazardous materials require special handling. Asbestos insulation wrapped every pipe in ships built before 1990. Workers in basic masks, far below Western safety standards, remove it by hand. Oil residue coats engine rooms inches thick. Fuel tanks supposedly emptied still contain deadly vapors. Last year, 17 workers died in Bangladesh yards from explosions and toxic exposure. This is dangerous work done by desperate men. The cutting begins at the bow. Workers climb scaffolding made from ship parts, wielding oxyacetylene torches, burning at 6,000 degrees. Steel glows cherry red, then separates. Chunks weighing tons crash onto beach sand, shaking ground felt hundreds of yards away. Watch the cutter teams. They work in pairs. One torches, one watches for falling debris. No hard hats. Flip-flops instead of steel-toed boots. Yet their precision is remarkable. They know exactly where to cut, following structural blueprints memorized through years of experience. The ship tells you where it wants to break, says one veteran. Fight the steel wins. Work with it, you go home alive. As the superstructure disappears, the real treasure emerges, the hull. This is where serious tonnage lives. Hull plates measure 1 inch thick, weighing hundreds of pounds per square foot. Cranes, themselves salvaged from previous ships, lift cut sections onto flatbed trucks. The steel heads to re-rolling mills within miles of the beach. Picture the economics. A scrapped container ship sells for $500 per ton. 60,000 tons equals $30 million, split between ship owner, yard owner, and workers earning $3 daily. The math seems cruel, but it's why these yards exist. No Western facility can compete with labor costs. Environmental regulations alone would triple expenses. The engine room reveals industrial archaeology. Marine diesels the size of houses, 12 cylinders, each taller than a man, get disassembled bolt by bolt. These engines ran continuously for 30 years, burning heavy fuel oil thicker than honey. The engineering is magnificent. Crankshafts weighing 50 tons, precisely balanced to spin at 100 RPM without vibration. This machinery doesn't get melted. It gets resold. Ship engines power factories across South Asia. Generators light villages without grid connections. Pumps irrigate farms. The secondary market for marine equipment employs thousands of traders, mechanics, and transporters. Nothing from a ship truly dies. It migrates into developing economies, extending useful life decades beyond original purpose. Below the waterline lies the double bottom, the ship's structural spine. These compartments held ballast water, fuel reserves, sometimes cargo. Accessing them requires cutting through multiple steel layers, descending into spaces never designed for human comfort. Workers joke darkly about the belly, where heat concentrates, air thins, and escape routes disappear. Cutting the double bottom takes weeks. Each section weighs tons, but must be removed carefully. Collapse here buries workers under steel avalanches. Supervisors watch from shore, tracking progress through radio calls. When sections finally break free, cranes swing them clear while workers scatter. The beach cheers each successful lift. These small victories accumulate into complete demolition over months. The propeller comes last and commands highest prices. Bronze propellers weighing 40 tons contain copper, aluminum, nickel, and manganese in precise alloy. Scrap value exceeds $200,000. Yards guard propellers like treasure, storing them in secured compounds until specialty metal dealers arrive. Watch the propeller removal. It requires precision cutting around the shaft, then carefully lowering the massive bronze flower onto reinforced trailers. One slip damages blades worth thousands each. The journey from beach to foundry happens under armed guard. Bronze theft funds criminal operations throughout the region. When finally melted, this propeller might become electrical wiring, plumbing fixtures, or musical instruments. The ship's heartbeat transforms into civilization's nervous system. Shipbreaking emerged from necessity after World War II. Hundreds of Liberty ships, hastily built for wartime cargo, became obsolete overnight. Scrapping them created the modern industry. Taiwan dominated through the 70s, then Korea, then China. Environmental regulations pushed the trade to South Asia by the 90s. Chittagong rose because geography cooperated. Extreme tidal ranges, 16 feet between high and low, create natural dry docks. Sandy beaches cushion impacts. Cheap labor, minimal regulation, and proximity to steel-hungry construction markets completed the equation. Today, Bangladesh breaks 40% of global tonnage. The industry employs over 200,000 workers directly, plus countless more in supporting trades. Love it or hate it, shipbreaking built modern Bangladesh. Carbon emissions dropped 62% using ship-sourced steel versus virgin ore production. Industry recycles 20 million tons of steel annually, enough to build 4,000 skyscrapers. A single aircraft carrier yields enough metal for 15 apartment towers housing 50,000 people. Here's the secret we promised. That ship doesn't just get recycled, it gets reincarnated completely. 95% of every vessel finds new life. Steel becomes rebar reinforcing buildings throughout Asia. Copper wiring powers homes. Furniture furnishes restaurants. Lifeboats become fishing vessels. Even the wooden decking becomes flooring in European boutiques, marketed as reclaimed teak at premium prices. From ocean voyager to urban infrastructure, the transformation completes. We've built an ecosystem where nothing truly disappears. That cruise ship where honeymooners danced might now support the hospital where their grandchildren are born. The container ship carrying your television might become the bridge you drive across. Ships don't die on those beaches. They scatter into civilization, becoming the hidden skeleton of modern life. Steel ghosts supporting everything we build.
Every second, 32 tires begin service worldwide. Each survives 100,000 miles of punishment, heat, friction, road impacts before replacement. Picture mountains of rubber growing daily. 2 billion tires manufactured annually, weighing 25 million tons combined. That's every car, truck, aircraft, and bicycle on Earth demanding fresh rubber constantly. How does liquid petroleum become indestructible black donuts? Why do old tires refuse to decompose for 500 years? Stick around. You'll discover the shocking chemical process transforming oil into immortal rubber and the jaw-dropping secret of where 85% of American worn tires end up. Hint? It's beneath your feet on football fields.
The story begins in Southeast Asian plantations, where rubber trees grow in geometric rows, stretching miles. Workers cut V-shaped grooves into bark, collecting milky latex sap in cups. Each tree produces 2 ounces daily, barely enough to fill shot glasses. Natural rubber comprises 30% of modern tires. The remainder uses synthetic alternatives derived from petroleum. Massive chemical plants crack crude oil into monomers, butadiene, styrene. then polymerize them into synthetic rubber matching natural properties. These facilities process 50,000 barrels daily, transforming black liquid into white crumb rubber. The similarity is uncanny. Petroleum-based rubber exhibits elasticity, strength, and durability rivaling million-year-old tree evolution. Chemistry replicates nature in months.
Next comes compounding, the secret sauce where rubber meets additives. Industrial mixers, standing 2 stories tall with rotors spinning at 80 RPM, blend rubber with carbon black, silica, sulfur, accelerators, and antioxidants. Carbon black, basically controlled soot production, reinforces rubber while providing characteristic black color. Without it, tires would be translucent white and fail within miles. Each tire compound contains 15 ingredients mixed in precise ratios. Tread rubber emphasizes durability. Sidewall rubber prioritizes flexibility. Inner liner uses butyl rubber for air retention. Formulations remain trade secrets. Michelin's compounds differ from Goodyear's, creating performance variations. Mixing takes 12 minutes at temperatures reaching 300 degrees Fahrenheit. The batch, weighing 500 pounds, emerges as uniform black mass ready for shaping.
Giant extruders force hot rubber through dies, creating continuous strips of tread, sidewalls, and bead filler. These machines operate like industrial Play-Doh shapers, pushing material through shaped openings at forces exceeding 2,000 psi. Tread emerges with grooves preformed. Sidewalls arrive as smooth sheets. Cooling conveyors solidify the profiles. Meanwhile, calendaring machines squeeze rubber sheets to precise thickness, measured in thousands of inches, coating steel cord and fabric plies. These textile layers provide structural strength. Modern radial tires contain steel belts running at 0 degrees to rotation direction, fabric plies at 90 degrees, creating cross-brace architecture. Workers cut these components into precise lengths, stockpiling thousands of parts daily for assembly lines demanding continuous supply.
Comes tire building, robotic ballet assembling 30 components into recognizable shapes. Cylindrical drums rotate while automated arms apply inner liner, body plies, steel belts, sidewalls, and tread in programmed sequence. Each component positions within 0.05-inch tolerance. Precision matters because imbalance at highway speeds creates dangerous vibrations. The green tire, uncured assembly, looks puffy and pale, lacking final tread pattern. Steel beads, wire bundles coated in rubber, anchor edges, providing mounting surfaces for wheel rims. These beads contain piano wire strength steel wound in continuous loops. Braking beads requires forces exceeding 5 tons, ensuring tires never separate from rims even during blowouts. Assembly takes 3 minutes per tire on modern automated lines, producing 2,000 tires daily.
Curing transforms green tires into finished products through heat, pressure, and chemistry. Massive presses, resembling medieval iron maidens, close around green tires. Internal bladders inflate with superheated steam at 350 degrees Fahrenheit and 200 psi. External mold segments, engraved with tread patterns, press inward simultaneously. This step is critical. Vulcanization. Sulfur atoms cross-link rubber polymer chains, creating 3-dimensional molecular networks. Picture chain-link fences welded together at every intersection. That's vulcanized rubber at molecular level. The process, discovered accidentally by Charles Goodyear in 1839, transformed useless sticky material into engineering marvel. Curing takes 12 minutes. Afterward, tires emerge rigid with crisp tread patterns and permanent shape. They'll never soften or melt again. Vulcanization is irreversible.
After curing, quality control begins. X-ray machines scan internal structure, detecting steel belt misalignment, air pockets, or ply separations invisible externally. Uniformity machines spin tires at highway speeds, measuring force variations. Even 0.5-pound imbalance causes rejection. Ship tires must perform flawlessly at 120 miles per hour for tens of thousands of miles. Inspectors examine tread depth, sidewall finish, bead seating. DOT codes stamped into sidewalls identify manufacturing plant, date, batch number, critical for recalls. Modern tires undergo durability testing. Machines simulate 50,000 miles in 72 hours, cycling through temperature extremes, overloading, underinflation. Failure rate must stay below 0.1%. That's one defective tire per 1,000, because tire failure at highway speeds kills people. Performance testing pushes limits beyond consumer use. Test drivers race prototype tires on proving grounds, executing emergency maneuvers, sustained high-speed runs, extreme weather conditions. Sensors measure temperatures, pressures, wear rates. Data feeds computer simulations refining compounds and construction. Winter tires use softer compounds, remaining flexible below freezing. Summer tires employ harder rubber, resisting heat degradation. All-season compromises performance for year-round versatility. Racing slicks sacrifice tread patterns for maximum contact area. Professional race tires last 200 miles but provide grip exceeding street tires tenfold. Tire engineering optimizes contradictory requirements: durability versus performance, comfort versus handling, cost versus longevity. Every design represents compromises, balancing physics against economics. This technology evolved from crude beginnings. Ancient Mesoamericans harvested rubber for balls and waterproofing 3,000 years ago, but material degraded rapidly. Charles Goodyear's 1839 vulcanization discovery changed everything. Accidentally dropping rubber sulfur mixture on hot stove created heat-stable material. The pneumatic tire emerged in 1888 when John Dunlop invented air-filled rubber tires for his son's tricycle. That innovation enabled automobile revolution. Cars needed shock absorption only inflatable rubber provided. Radial tire construction, invented by Michelin in 1946, improved durability 50% over bias ply designs. Today's run-flat tires, self-sealing compounds, and airless prototypes continue evolution. Annual global production exceeds 2 billion units, creating waste management crisis demanding solutions. Carbon emissions drop by 62% using recycled tire crumb versus virgin rubber production. Industry saves over $41 billion annually through tire recycling. Processing old tires into crumb costs 70% less than manufacturing new rubber from petroleum. So here's the secret. 85% of American-worn tires avoid landfills through recycling programs. Shredders reduce tires to fingernail-sized crumb. This material becomes artificial turf infill, those black granules beneath football field grass that cushion impacts and improve drainage. Schools, parks, and stadiums nationwide walk on recycled tires daily without knowing. Crumb rubber also creates playground surfaces, running tracks, asphalt modifiers, improving road durability 20%. From petroleum to pavement to playing fields, cycle completes. Tires never die. They transform. That indestructible black donut refusing decomposition becomes humanity's accidental gift to circular economy. We've learned that immortal materials demand eternal responsibility.
More than half of Earth's entire weight is iron, 32% of the planet's mass. Earth's core is a gigantic ball of molten iron the size of the moon. But iron rules on the surface too. Every second, humanity produces 60 tons of steel, 2 billion tons per year. That's more than all other metals combined. 95% of all metal used by civilization is iron and steel. Without iron, there'd be no skyscrapers, bridges, ships, cars, or trains. How do fiery rivers of molten metal at 3,600 degrees emerge from red ore in city-sized quarries? You'll see explosions in quarries, blast furnaces as tall as 30-story buildings, converters where oxygen turns pig iron into steel in minutes, and rolling mills where 1,000-ton slabs get rolled into paper-thin sheets. Watch to the end. The finale shows why iron holds the world together. This is the story of the metal that built civilization.
The Lebedensky Quarry in Russia is one of the planet's largest iron ore quarries. Depth, nearly 2,000 feet. Width, 3 miles. From the edge, you can't see the bottom. A gigantic wound in the earth from which 100,000 tons of iron ore are extracted daily. Excavators as tall as 10-story buildings scoop rock with buckets holding 1,800 cubic feet. One bucket is like a small house. Dump trucks with 360-ton capacity haul ore up the spiral road. Wheels taller than a person. But before loading the ore, it needs to be blasted. Drilling rigs create holes 65 feet deep. Tons of ammonium nitrate explosive are packed into these holes. The explosion? Earth trembles. A wall of rock tall as a skyscraper crashes down. A dust cloud rises 3,000 feet. After the dust settles, excavators begin work. The ore is reddish-brown, sometimes almost black. Magnetite and hematite, iron oxides. Iron content ranges from 30 to 60%. The rest is waste rock.
The ore goes to a processing plant. Massive cone crushers grind bus-sized chunks. The noise can be heard for miles. Ore gets crushed to fist size, then to gravel, then smaller. It enters ball mills, steel drums 20 feet in diameter, 33 feet long. Inside are hundreds of tons of steel balls. The drum rotates, balls drop, grinding ore into fine powder. After 8 hours of grinding, you get reddish-brown dust. It's mixed with water, creating pulp, liquid slurry. This slurry passes through magnetic separators. Magnetite sticks to magnetic drums. Waste rock washes away. The concentrate contains 65 to 70% iron. From this, they make pellets, granules the size of walnuts. Wet concentrate gets rolled into balls on special drums, then fired at 2,400 degrees Fahrenheit. Pellets harden, becoming rock solid. These pellets are raw material for blast furnaces. Each plant produces millions of tons of pellets yearly. They're loaded onto trains and shipped to steel mills. A blast furnace is a steel tower 330 feet tall, 46 feet in diameter. 30 stories of pure metal and fire. Lined inside with 3-foot-thick fireproof brick. Internal volume, 176,000 cubic feet. Iron ore pellets, coke, and fluxes like limestone or dolomite are loaded from the top, in layers, like a layered cake. Several hundred tons at a time. From below, through tuyères, openings in the walls, hot air is blown in. Air temperature, 2,200 degrees Fahrenheit. Pressure, 4 atmospheres. Coke ignites. Temperature in the furnace's lower section reaches 3,600 degrees Fahrenheit. Pellets slowly descend, heating up. Different reactions occur at different heights. First, moisture leaves the ore. Then, at 930 degrees, iron oxide reduction begins. Carbon from coke strips away oxygen. At 1800 degrees, ore becomes spongy iron. At 2700 degrees, iron melts. Drops of molten metal flow down. At the furnace bottom, molten pig iron accumulates, an iron alloy with 4% carbon. Pig iron temperature at the furnace bottom is 2,700 degrees Fahrenheit. It glows blindingly white with an orange tint. Pig iron is denser than slag, so it stays at the bottom. Slag, molten impurities and fluxes, floats on top. Every 4 hours, they open the tap hole, an opening in the furnace's sidewall. Pig iron tapping is a fire show. A stream of molten metal flows down channels. Sparks fly dozens of feet. The brightness requires dark glasses to watch. Pig iron flows into massive ladles on railroad cars. One ladle holds 300 tons. It's a locomotive made of molten metal. The ladle gets covered to prevent cooling and shipped to the steelmaking shop. One blast furnace operates continuously for years. Stopping is catastrophic. Metal would solidify inside. The furnace produces 10,000 tons of pig iron daily. That's like 100 railroad cars. Major steel mills have 10 to 15 blast furnaces. But pig iron isn't steel yet. It's brittle due to high carbon content. Steel is needed, an alloy with less than 2% carbon. Pig iron gets poured into a converter, a massive pear-shaped vessel 33 feet tall, lined with fireproof brick. It holds 350 tons of molten metal. The converter tilts, pig iron pours in, steel scrap is added for cooling. The converter returns to vertical position. An oxygen lance, a tube 20 inches in diameter, lowers from above. Oxygen flow begins. A jet of pure oxygen at 150 pounds per square inch pressure strikes the molten metal. Violent reaction begins. Oxygen oxidizes carbon, silicon, manganese, impurities in pig iron. These exothermic reactions release enormous heat. Temperature rockets to 3,200 degrees Fahrenheit. Metal boils and churns. Flame tongues several feet high shoot from the converter mouth. Sparks and molten drops fly everywhere. The blowing process takes 20 minutes. In this time, 350 tons of pig iron become steel. Carbon burns down to 1% or less. The converter tilts, steel pours into a ladle. The molten metal glows blindingly white at 2,900 degrees Fahrenheit. Alloying elements get added to the ladle. Manganese, chromium, nickel, molybdenum, depending on the steel grade needed. They mix it by blowing argon through. Then steel gets cast. There are 2 methods. First, continuous casting. Molten metal pours into a crystallizer, a water-cooled copper mold. Below, a solidifying blank emerges, a slab 8 inches thick, 6.5 feet wide. It glows red, surface temperature around 1,800 degrees Fahrenheit. Gas cutters slice the slab into 33-foot lengths. One slab weighs 25 tons. Second method, casting into ingot molds. Steel forms. This creates ingots up to 50 tons. These ingots and slabs are semi-finished products. They go to rolling mills. There begins the final transformation, turning thick blanks into thin sheets, rails, or beams. Slabs heat in reheating furnaces to 2,200 degrees Fahrenheit, red hot. Then they go to the rolling mill. It's a line of dozens of rolls. Steel cylinders 3 feet in diameter weighing dozens of tons. Rolls rotate toward each other. The red-hot slab enters between rolls. They squeeze and roll it. The slab gets thinner and longer. It passes through the next pair of rolls, even thinner, dozens of times. An 8-inch thick slab becomes a sheet 1 to 2 millimeters thick. Length grows from 33 feet to over half a mile. Rolling speed on finishing mills reaches 50 miles per hour. Red-hot steel ribbon flies through the mill, sparks flying everywhere. Temperature drops to 1,400 degrees Fahrenheit, metal darkens. The strip cools with water, winds into giant coils weighing 20 to 30 tons. This is hot-rolled steel, the foundation for car bodies, appliance housings, building structures. Global steel production is 2 billion tons yearly. China produces over 1 billion tons, half the world's output. India, Japan, the US, Russia are other major producers. Steel is infrastructure's backbone. 95% of metal structures are steel, from skyscrapers to tin cans, from tankers to paper clips. Iron and steel are civilization's skeleton. Iron is the oldest metal after copper and bronze. The Iron Age began 3,000 years ago. First, iron came from meteorites, ready-made metal fallen from the sky. Egyptian pharaoh Tutankhamun was buried with a meteorite iron dagger. Smelting iron from ore was learned by Hittites in Asia Minor around 1200 BC. They kept the secret for centuries, but technology spread. Iron weapons were stronger than bronze. Iron plows worked soil better than wooden ones. Civilizations with iron defeated civilizations without iron. Medieval times, iron was made in small furnaces. The Industrial Revolution began with blast furnace invention in the 18th century. Early furnaces used charcoal. Later, they switched to coke from coal. The 19th century brought the converter process, rapid pig iron to steel conversion. Bessemer, Martin, Thomas, names that changed the world. The 20th century was steel century. Skyscrapers, bridges, ships, automobiles. Without steel, there'd be no modern world. And so, traveling from explosions and 2,000-foot-deep quarries through giant crushers and magnetic separators, through 300-foot-tall blast furnaces at 3,600 degrees and converters where oxygen burns out carbon in 20 minutes, through rolling mills where 8-inch slabs become millimeter-thin sheets, steel emerges, the metal that built civilization. 2 billion tons per year. 60 tons every second. The metal everything around us is made from. Every skyscraper, every bridge, every car, every ship. It's iron, mined from red ore, remelted in fire, rolled into sheets. More than half of Earth's weight is iron. The planet's core is molten metal. And on the surface, iron rules. 95% of all metal is iron and steel. From nails to bridges, from paper clips to skyscrapers, iron holds the world together. Without iron, humanity would collapse back to the Stone Age. No machines, no electricity, no internet. Everything's built on iron. From fiery rivers of molten pig iron in blast furnaces to steel beams holding up skyscrapers, iron is the foundation, the base, civilization's skeleton. Metal of the gods that became metal of the masses. The most abundant, most important, most irreplaceable. Iron, the metal that holds the planet together. Every day, somewhere in China, a machine generates force equivalent to stacking 200 fully loaded aircraft carriers vertically. This hydraulic press, rated at 80,000 tons, stands 10 stories tall and weighs more than the Eiffel Tower. Picture this. Under its ram, 300-ton steel billets, weight of 60 elephants, flatten like modeling clay in seconds. The ground shakes for miles when it operates. Windows rattle in villages 8 miles distant. How does humanity create machines powerful enough to reshape mountains of metal? Why did Cold War superpowers race to build ever larger presses? Stick around till the end. You'll discover the jaw-dropping reason these monster machines dominate aerospace and defense, the shocking physics of what happens when 80,000 tons compress glowing steel, and why welding became obsolete for the world's most critical components. The story begins at China Erzong Group in Deyang, Sichuan Province, home to the world's most powerful forging press. This colossal machine, commissioned in 2013, towers 120 feet tall. Picture a 12-story building dedicated to squashing metal. The press frame alone weighs 22,000 tons, constructed from steel beams thicker than telephone poles, bolted together with fasteners weighing 500 pounds each. The facility consumes electricity equivalent to 40,000 homes during operation. 8 separate hydraulic power units, each the size of shipping containers, pump oil through pipes 16 inches in diameter.
These hydraulic systems generate pressures reaching 10,000 psi, enough to blast water through concrete like tissue paper. When all systems activate simultaneously, the combined oil flow measures 3,000 gallons per minute. That's emptying a backyard swimming pool every 10 minutes continuously through hydraulic cylinders generating incomprehensible force. Next comes the press bed, a foundation descending 60 feet below ground level, deeper than 6-story buildings are tall. This isn't merely concrete, it's a geological anchor. Engineers excavated solid bedrock, then poured 8,000 cubic yards of reinforced concrete mixed with steel rebar, forming 3-dimensional cages. The foundation weighs 45,000 tons, more than 4 nuclear submarines combined. Why such extreme engineering? Because when 80,000 tons of force compress metal, Newton's third law demands equal reaction force pushing downward. Without this massive foundation, the press would crack bedrock and sink into earth like a nail hammered into butter. Seismographs detect vibrations from press operations 12 miles away, not from noise, but from actual ground displacement. The Chinese government prohibited residential construction within 2-mile radius specifically because repeated press cycles could damage building foundations through accumulated seismic stress over years. Giant overhead cranes, rated at 600 tons capacity and spanning widths exceeding football field lengths, position workpieces beneath the ram. These cranes represent engineering marvels themselves, structures where every rivet matters because failure means dropping cargo worth millions. Control rooms, protected by 18-inch thick reinforced concrete walls and bulletproof glass windows, house operators controlling machinery from safe distances. The press ram, the actual crushing surface, measures 40 feet by 30 feet, larger than most studio apartments. Made from tool steel hardened to withstand pressures that would pulverize normal steel, this ram surface gets replaced every 18 months despite costing $2 million. Replacing it requires 3 weeks of round-the-clock work using specialized welding techniques and stress relief treatments. Even with hardened steel, repeated impacts against 300-ton billets create microscopic cracks propagating until failure becomes inevitable. Now comes forging, industrial violence at physics-defying scales. Workers heat steel billets to 2,400 degrees Fahrenheit in furnaces consuming natural gas at rates measured in tons per hour. At these temperatures, steel glows brilliant orange and becomes plastic, deformable under pressure but not liquid. Picture clay that weighs more than locomotives and requires forces exceeding aircraft carrier displacement to reshape. Overhead cranes lower glowing billets onto the press bed with precision measured in inches, despite handling weights where inches of error cause catastrophic collisions. The ram descends at speeds reaching 20 inches per minute. Sounds slow until you realize 80,000 tons moving at any speed generates momentum requiring precise hydraulic control. One malfunction, one stuck valve, one pressure spike, and the ram becomes an uncontrollable projectile carrying enough energy to demolish the entire facility. The compression itself defies description. As the ram contacts glowing steel, metal begins flowing, literally flowing despite being solid. Under 80,000 tons of pressure, crystal structures collapse and reorganize. Grains elongate perpendicular to compression direction, creating oriented microstructures impossible to achieve through casting. The billet spreads outward, metal squeezing into die cavities with force sufficient to emboss details smaller than human hair thickness. This step is critical because forging aligns crystal boundaries, eliminates porosity, and creates grain flow patterns following component geometry. Cast parts contain random crystal orientations and microscopic voids. Forged parts exhibit continuous crystal structures and zero internal defects. That's the difference between components failing under stress versus components exceeding design specifications. Hydraulic systems monitor pressure continuously. Deviations exceeding 1% trigger automatic shutdown.
because overpressure shatters dies costing millions, while underpressure produces weak forgings requiring scrapping. After initial compression, the workpiece requires reheating and multiple press cycles. Large forgings need 20 to 40 separate compressions, each reshaping metal incrementally. Between cycles, manipulators, robotic arms capable of rotating 300-ton workpieces, reposition the forging. These manipulators exert forces exceeding 500 tons merely to rotate incandescent metal safely. Picture this: the forging process for a single large component spans 2 weeks. Workers cycle the workpiece between furnace and press 40 times, gradually transforming a rectangular billet into complex shapes: bulkheads for aircraft fuselages, rocket motor casings, pressure vessel heads. Each press cycle compresses the forging 3 to 6 inches, permanently deforming metal through controlled violence. Temperature control matters critically. Too hot, metal oxidizes excessively. Too cold, it cracks under pressure. Operators monitor color constantly, making decisions affecting millions in material value based on visual assessment of orange to red glow transitions. Quality control begins before forging even starts. Ultrasonic inspection systems scan billets, searching for internal defects invisible to naked eyes. Even microscopic inclusions, slag particles, oxide stringers, sulfide formations, become stress concentrators, causing catastrophic failure in finished components. Rejected billets return to steel mills for remelting. After forging, dimensional inspection using laser scanning creates three-dimensional models accurate to thousands of inches across components 30 feet long. Metallurgical testing cuts samples from forging edges, examining grain structure through electron microscopy. Grain size, orientation, boundary spacing, all must meet specifications tighter than semiconductor manufacturing tolerances. Modern aerospace forgings require grain sizes smaller than 0.005 inches, with elongation ratios exceeding 10 to 1. Without precise microstructure control, components fail unpredictably during service, potentially causing catastrophic accidents. This technology race began during Cold War paranoia. In 1955, the Soviet Union commissioned a 75,000-ton press at Novokramatorsk specifically for forging submarine hulls and missile casings. American intelligence discovered this capability through spy satellite photographs showing the massive building housing it. President Eisenhower immediately authorized construction of matching presses. The Air Force Heavy Press program built 12 presses between 1956 and 1959, including twin 50,000-ton giants at Alcoa and Wyman Gordon. These presses enabled Boeing 707 and later jumbo jets. Without them, aircraft manufacturers couldn't produce wings large enough. The strategic logic was brutal. Whoever controlled large forging capacity controlled aerospace dominance. Nations without heavy presses bought components from competitors, creating national security vulnerabilities. China entered this arena late but decisively. Their 80,000-ton press, exceeding any Cold War relic, announced intentions clearly: aerospace independence. Today, China produces aircraft landing gear, rocket stages, and turbine components previously imported from America and Russia. The press paid for itself within 5 years through import substitution alone. Carbon emissions drop by 43% when forging replaces welded assembly in aircraft structures, eliminating welding energy and reducing weight through integrated designs. Industry saves over $32 billion annually through large forgings versus machining components from solid billets, which waste 90% of material as chips. Processing costs drop 61% because one forging operation replaces dozens of machining hours. So here's the secret promised: these monster presses exist because physics favors size. Larger presses forge larger components in single operations, eliminating joints where failures initiate.
Every weld introduces heat-affected zones with altered crystal structures becoming crack paths. Every bolted joint adds weight and complexity. Seamless forgings eliminate these vulnerabilities entirely. That's why the Airbus A380's wing ribs come from single forgings. No welds, no joints, just continuous metal flowing across 20-foot spans. From Cold War arms race to commercial aerospace dominance, cycle completes. The 80,000-ton press represents more than manufacturing capability. It's geopolitical leverage. Nations with these machines build aircraft, rockets, submarines independently. Nations without them remain customers, technologically dependent, strategically vulnerable. We've learned that industrial capacity determines global power hierarchies as surely as nuclear arsenals. That press standing in Sichuan doesn't just forge metal, it forges national sovereignty. Every second, jet engines spinning at 12,000 revolutions per minute thrust hundreds of passengers across continents. But here's what defies physics. Inside those engines, turbine blades made of nickel alloy operate at 3,000 degrees Fahrenheit, temperatures exceeding their own melting point by 200 degrees. Picture holding ice cubes in boiling water without them melting. That's the metallurgical miracle happening 35,000 feet above your head. How does metal survive temperatures that should liquefy it? How do engineers grow crystals larger than your hand from molten metal? Stick around till the end, you'll discover the jaw-dropping secret of single crystal manufacturing that eliminated metal's greatest weakness, and why a single turbine blade costs more than your car yet lasts 20 years in literal hell. The story begins in specialized foundries where clean room standards rival semiconductor fabs. These facilities maintain air purity of less than 100 particles per cubic foot, 10,000 times cleaner than normal atmosphere. Even microscopic dust particles cause catastrophic flaws in turbine blades spinning at speeds where centrifugal forces generate stresses exceeding 70,000 pounds per square inch. That's pressure crushing steel like aluminum foil. Workers suit up in full-body cleanroom gear before entering casting halls. Inside, massive vacuum furnaces standing 2 stories tall and weighing 80 tons create environments replicating outer space. Vacuum pumps evacuate air until pressure drops to 1/1,000,000th of atmospheric pressure. At these conditions, materials behave differently. Impurities vaporize instantly. Gases trapped in metal escape, leaving behind purity impossible at normal pressure. Processing single batches costs $50,000 in electricity alone. Next comes mold preparation, where ceramic shells, think pottery on steroids, get built layer by microscopic layer. Technicians dip wax patterns shaped like turbine blades into ceramic slurry 10 times, waiting hours between coats. Each layer adds thickness thinner than human hair. After 20 days of coating and drying, workers melt wax away in autoclaves, leaving hollow ceramic molds with internal channels more complex than human circulatory systems. These molds contain passages narrower than spaghetti strands, designed to cool blades from inside during operation. Some channels measure just 0.008 of an inch across, thinner than credit cards. Manufacturing these passages requires such precision that lasers verify every dimension. One blocked cooling hole means blade failure at 300 degrees lower temperature. That's difference between safe flight and catastrophic engine disintegration at cruise altitude, scattering turbine fragments through fuselage like shrapnel.
Giant crucibles containing nickel-based superalloy. Mixtures of nickel, chromium, cobalt, aluminum, titanium, plus 6 other elements in exact proportions. Heat to 2,700 degrees Fahrenheit. Picture liquid metal glowing white like miniature stars captured in ceramic containers. This superalloy, developed through decades of research, contains more expensive elements per pound than fine jewelry. A single turbine blade uses materials costing $800 before any manufacturing begins. Robotic arms lower ceramic molds into this molten inferno with precision measured in thousandths of inches. Timing matters critically here. Pour too fast, turbulence creates defects. Too slow, metal solidifies prematurely. Furnaces tilt at exactly 2 degrees per second, filling mold cavities in 17 seconds. During this pour, metal temperature drops 300 degrees, requiring computer-controlled heating to maintain consistency. One temperature fluctuation of 5 degrees ruins the casting, wasting months of preparation.
Now comes the magic, directional solidification. The filled mold sits atop a water-cooled chill plate at 70 degrees Fahrenheit while surrounded by heating elements maintaining 2,400 degrees above. This creates the steepest temperature gradient in metallurgy, over 2,000 degrees difference across 6 inches. That's transitioning from Arctic to volcanic conditions in the space between your thumb and pinky. Slowly, incredibly slowly, a computer-controlled mechanism lowers the mold through the furnace at speeds of 6 inches per hour. Picture watching paint dry, then slowing that down tenfold. As the mold descends, metal solidifies from bottom upward in a razor-thin freezing front. This directional cooling forces crystal growth in one direction only, upward, eliminating horizontal grain boundaries where cracks normally form. The process takes 14 hours for a 4-inch blade. Rush it by even 10% and polycrystalline grains form, destroying blade strength. But here's where physics becomes art. At the mold bottom sits a grain selector, a corkscrew-shaped passage so narrow only one crystal nucleus fits through. As metal solidifies upward, countless tiny crystals form at the chill plate. They compete, growing upward like metallic trees racing toward sunlight. Most hit the spiral walls and stop. Only the perfectly aligned crystal, the one matching the spiral's orientation, passes through this metallurgical gauntlet. This step is critical because it ensures the entire blade, every atom from root to tip, belongs to one continuous crystal lattice. No grain boundaries exist anywhere. Normal metals contain millions of grain boundaries per cubic inch. Single crystal blades contain 0. Without boundaries, there are no weak spots where atoms slip past each other under stress. The crystal structure extends uninterrupted through the entire blade like a 3-dimensional molecular Kevlar vest, with atoms locked in perfect geometric formation. After solidification, blades undergo solution heat treatment at 2,200 degrees Fahrenheit for 2 hours, then quench in inert gas. This locks crystal structure permanently and precipitates microscopic strengthening phases throughout the lattice. Next comes aging heat treatment, multiple cycles at precisely controlled temperatures that cause nanoscale particles to form. These particles, called gamma-prime precipitates, occupy 70% of the alloy's volume. Picture this. Imagine a 3-dimensional checkerboard where hard particles pin the crystal lattice, preventing atoms from sliding. These precipitates remain stable at temperatures where other metals liquefy. They're the secret allowing nickel alloys to maintain strength at 3,000 degrees, temperatures where aluminum vaporizes, titanium melts, and even steel becomes taffy. The heat treatment process takes 96 hours of precise temperature control. Deviate by 15 degrees at any point and mechanical properties drop 40%.
Coating application transforms already sophisticated blades into thermal protection systems. First, a metallic bond coat, aluminum-rich alloy, gets applied via high-velocity plasma spray at 20,000 degrees Fahrenheit. Metal particles accelerate to twice the speed of sound, impacting the blade surface with such force they cold weld instantly. This creates a rough surface for subsequent layers while providing oxidation resistance. Then comes the thermal barrier coating. Yttria-stabilized zirconia ceramic applied atom layer by atom layer using electron beam physical vapor deposition. In vacuum chambers, electron beams vaporize ceramic ingots. The vapor condenses on rotating blades, building up a coating 0.08 of an inch thick with a columnar microstructure full of microscopic pores. These pores act like thermal insulation, trapping air pockets that reduce heat transfer. The ceramic coating lowers blade temperature by 400 degrees, the difference between survival and meltdown. Modern engines couldn't exist without this coating technology. This wasn't always possible. Back in 1940, early jet engines used cast iron turbine blades lasting 20 hours before failure. Temperatures barely reached 1,400 degrees Fahrenheit. The breakthrough came when Pratt & Whitney researcher Frederick Vierling invented directional solidification in 1966, eliminating transverse grain boundaries and doubling blade life overnight. The true revolution arrived in 1982 when General Electric and Pratt & Whitney independently perfected single crystal casting. Turbine inlet temperatures jumped from 2,000 degrees to 3,000 degrees Fahrenheit, a 50% increase enabling massive efficiency gains. Modern turbofan engines achieve fuel efficiency triple that of 1960s designs. Today, advanced engines like the GE9X powering Boeing 777X aircraft operate at 3,200 degrees, with pressure ratios reaching 60:1. These engineering advances cut aviation fuel consumption by 65% per passenger mile over 50 years. Carbon emissions dropped by 12% when replacing older turbine blades with modern single crystal versions in existing engines, equivalent to removing 18 million cars annually from global fleets. Airlines save over $47 billion yearly through improved fuel efficiency. Maintenance costs drop 58% because single crystal blades last 3 times longer than conventional ones. So here's the secret promised. These blades don't actually survive above their melting point through material strength alone. They're actively cooled by air bled from the compressor, flowing through those microscopic internal channels at supersonic speeds. This cooling air, already compressed to 400 degrees Fahrenheit, seems hot by human standards but runs ice cold compared to the 3,000-degree combustion gases outside. Combined with ceramic coatings reflecting heat like mirrors, the actual metal temperature stays below 2,000 degrees, hot enough to glow orange but survivable. From molten metal to flying miracles, cycle completes. Single crystal turbine blades represent humanity's most sophisticated metal casting achievement. Objects where every atom's position matters, where crystal orientation determines survival, where manufacturing tolerances make computer chips look crude. We've engineered metal to survive in conditions nature never intended, creating materials that work at their physical limits. That's not just manufacturing. That's molecular architecture enabling the modern world's ability to shrink distance itself.